For the primary bow, the angle between the direction of the sunlight and the emerging ray was around about 42 degrees. But if the light is reflected twice, the concentration of emerging rays occurs at an angle of about 51 degrees to the sunlight. In other words, as light enters all around the front of the drop, the second reflection gives a wider cone than the one which forms the primary. Including the different colours, you get another nest of cones emerging from the raindrop. This time the violet cone is outermost. This second set of cones being outside the first set means that the secondary bow is outside the primary. The second reflection also reverses the colour order of the rays. At very high points in the cloud, the cones formed by the second reflection in the raindrops won't hit your eye. But moving further down, there comes a point where light from the bottom edge of the violet cone reaches your eye, so this is a region of cloud where drops appear violet. Further down again, drops appear green because it's the green cones which reach your eye. And finally, when the drop is further down still, it's only the edge of the innermost red cone which reaches your eye, so drops here appear red. Cones from all the other drops combine to complete the secondary bow. Look again at the graphs for 1 and 2 internal reflections. The light which undergoes one internal reflection emerges at angles up to 42 degrees, with a concentration between 40 and 42 degrees. Scattered light, below 40 degrees, is shown in grey. The light which has undergone 2 internal reflections emerges at angles from around 51 degrees and above, with a concentration at about that angle. So there's no light emerging from the raindrop between those angles. This implies that the region of sky in between the two bows should be less bright. You only see the relatively dark background cloud in this region. Indeed, there is a phenomenon known as Alexander's dark band, named after Alexander of Aphrodisias, who discovered it in 200 AD. This is a dark area of sky which lies between the two bows of the rainbow. This is yet another of the properties of the rainbow that can be explained by the mathematical model built up by the work of Aristotle, Descartes, and Newton. But the story of the rainbow isn't over yet. There are further phenomena which fascinate even today's scientists and mathematicians. For example, the so-called supernumeraries. If you look very carefully, you can sometimes see additional, very faint coloured arcs beneath the primary bow, which are not explained by our current model. To explain those, you need to revise the model, and that revision involves considering light as waves rather than straight rays. We've looked at a range of different models of the rainbow and the phenomena they explain. Aristotle's model, and his idea that all points in the rain cloud return light in a cone at a fixed angle, explained the rainbow's circular shape. Descartes' consideration of the behaviour of sunlight inside individual raindrops explains why there is a fixed angle, and also the presence of the secondary bow. Newton discovered that different colours are refracted slightly differently, and so explained the separation of the colours in the bows. And more recent work, using the wave model of light, has helped to explain the presence of the supernumeraries. But rainbow enthusiasts wouldn't be entertained if there weren't further questions to think about and more phenomena to see. If you can get a second internal reflection, you can get a third, a fourth, and so on. Usually you don't see the bows formed from this light, because you have to look through the rain cloud towards the sun to see them.